What causes self-referential loops in mathematical paradoxes? Imagine a puzzle where a statement keeps talking about itself, causing a never-ending cycle. That's what happens in some mathematical paradoxes, and it's fascinating to see how it all works. Self-referential loops happen when a statement, set, or system refers back to itself, directly or indirectly. This creates a cycle of references that can lead to contradictions or confusing results. Think of it like a mirror reflecting another mirror endlessly. These loops happen because the object tries to include or describe itself within its own definition, which can break the rules of logic and set theory. For example, consider the sentence, "This sentence is false." If it is true, then it must be false. But if it is false, then it must be true. This simple sentence creates a loop that confuses the mind and causes a paradox. It's a perfect example of how self-reference can cause logical contradictions. In the world of numbers and sets, self-referential loops often appear through sets that include themselves or functions that apply to themselves. Russell's paradox is a famous case. It asks if the set of all sets that do not contain themselves exists. If it does, then it must contain itself, but if it does not, then it must not contain itself. This contradiction shows how unrestricted self-reference can cause problems in naive set theory. More formally, these paradoxes can be explained using logical conditions where a set or property is defined by a rule that refers to itself. For instance, a set might be defined as all sets that do not contain themselves. If such a set exists, it must both contain and not contain itself, which is impossible. This creates a loop that can't be resolved. The core reason for these loops is that the systems or languages involved allow entities to include or describe themselves without any hierarchy or restrictions. To prevent these issues, mathematicians have created rules. For example, Zermelo-Fraenkel set theory limits how sets can contain themselves, and type theory introduces levels to avoid circular definitions. Self-referential loops also appear in logic and computer science. Curry's paradox, for example, involves a statement that says if it is true, then something absurd follows. This leads to contradictions because the statement refers to itself and tries to prove something impossible. Another example is the halting problem, which shows that no computer program can decide if any other program will stop running. It uses self-reference to prove that some questions are impossible to answer with certainty. When it comes to numbers and their meanings, these loops reveal how simple self-reference can create complex patterns and surprising limitations. They show that numbers, sets, and logical statements can encode self-referential ideas, leading to both interesting puzzles and fundamental challenges in mathematics. These loops are not just curiosities. They help us understand the boundaries of what can be logically and mathematically proven. In short, self-referential loops in mathematical paradoxes happen because entities refer to themselves, creating circular definitions that break the rules of logic. They expose the delicate balance between expressing ideas freely and maintaining consistency in mathematics and logic.